steps. So most chemical reactions do not occur in a single step, but they actually occur over a series of several different steps. So what you see is kind of the summary of a bunch of different steps that were taken to make this overall reaction happen. When we write a chemical equation to represent a reaction, we usually represent the overall reaction and not the individual steps. Here in this section, we're going to talk about the mechanism to get us to that end goal. So consider the following reaction of hydrogen reacting with iodide monochloride to form hydrochloric acid and iodide gas. The overall equation shows only the substances present at the beginning of the reaction and the substances formed by the reaction. It does not show the intermediate steps. The reaction mechanism is a series of steps individually which an overall chemical reaction occurs. So here, the proposed mechanisms are the following. We have these two steps. Hydrogen and iodide monochloride would first form hydrogen iodide and hydrochloric acid. Then the hydrogen iodide would be super unstable and react with iodide monochloride to form hydrochloric acid again and iodide gas. So what you notice in the first step is that the hydrogen molecules collide with the iodide monochloride molecules and forms these two products. But in the second step, you see that the hydrogen iodide collides again with a second iodide monochloride to form hydrochloric acid and iodide gas. Each step here is called an elementary step. Elementary steps are the individual steps in a reaction mechanism. They cannot be broken down into simpler steps. So these are the most simple steps possible for this type of mechanism. One of the requirements for a valid reaction mechanism is that the individual steps in the mechanism add to the overall reaction. So let's see here. Would this give us our overall reaction? Well, I'd be left with H2 plus 2 iodide monochlorides. My hydrogen iodide would cancel out. I have 2 hydrochloric acids and 1 iodide gas. So now that's my way of proving that this mechanism was correct because I summed up to my overall reaction. Notice that the hydrogen iodide molecule appears that it formed in one step and got consumed in the other. That's called a reaction intermediate. So a reaction intermediate forms in one elementary step and is completely then consumed in another. The reaction mechanism is complete here in a detailed description on the molecular level of what happens when, again, we're taking into account the different collisions and energy that we've talked about. But how do we determine a reaction mechanism? So now we're going to talk about the different steps that you would take to determine a reaction mechanism. So just to break down the mechanisms a little bit more. So reactions may occur all at once or through different steps. So just because we're saying that there's a reaction mechanism, it doesn't mean that every single equation that you see has a mechanism. They may occur all at once, like one collision, boom, there you are, there's your product, or you have several different steps. Each of these processes is known as an elementary reaction or elementary step. The sequence of these steps brings you your mechanism. We have intermediates that are species that appear in the reaction mechanism but not in the overall reaction. Hydrogen iodide did not appear in our reaction but it appeared in 2 steps. An intermediate specifically is formed in one step and then immediately consumed in the other. It aids the process of the reaction mechanism, but it is not an overall reactant or product in the equation in the end. You have different reactions that you can see. You have a unimolecular reaction. We know that when you have A goes to products, our rate is the rate constant times the concentration of the reactant. Or when you have multiple A and B, that would be rate constant times both concentrations of the reactants. If you have the same reactant, we simplify that by saying that reactant squared. So these are little tricks because this comes in handy when we're using a reaction mechanism to find the rate law. So writing plausible reaction mechanism, in order for us to say that this reaction mechanism works, we have to sum up all the elementary steps and they have to give us our overall reaction. That's a way of proving that this reaction mechanism is plausible. Another one is that the rate determining step should predict the rate law that is determined experimentally. Remember how we can only determine the rate law experimentally. Now, we can create a reaction mechanism and say that this is plausible if the rate determining step gives us the same rate law that we found experimentally. So those two factors help prove if a reaction mechanism actually works. The sum of the elementary step and that the rate law from the rate determining step is the same one from experimentally found. Now, what is the rate determining step? The rate determining step is the slowest step in the sequence of steps leading to product formation. Now, let's talk about that a little bit more. In most chemical reaction, one of the elementary steps is called the rate determining step. This step is much slower than the others. The rate determining step in a chemical reaction is similar to if you think of the narrowest section on a freeway. So if a section of the freeway narrows from 4 lanes to 2 lanes for even a short distance, right? Think of like there's a little part on the freeway that's blocked off because of construction, right? So from 4 lanes, it went into 2 lanes, but just a short period of time. The rate at which the cars travel along the freeway is now limited by the rate at which they can travel through that narrow section. Because now it's going to happen a little bit slower because of going from 4 lanes to 2 lanes, that slow section keeps it from going a lot faster. Even though the rate might be faster with the 4 lanes, since those 2 lanes are in the picture, we have to actually look at the rate at which those cars will move, taking into account the slow little section right there. So this basically is saying that if I wanted to know how much it would take me to get from point A to point B, I have to take into account that slow section of the freeway because I have to use it. So it's not accurate if I just use saying it's just going to be this pathway. I have that pathway that is a little bump in the road, which slows me down, so I have to use that to give me my most accurate time of getting to my destination. So the rate determining step in a reaction mechanism limits the overall rate of the reaction. And therefore, we use the rate determining step to determine the rate law of the overall reaction because it tells us what's limiting to the overall rate, right? It's giving us the most accurate information. Now, something I want to mention is that rate determining and rate limiting is the same exact thing. You'll see both of those terms thrown around in your book and in chemistry. The rate limiting step in a reaction mechanism limits, just like the limiting reactant, right? Limits the overall rate of the reaction, just like we're limiting to move forward when we have to go to 2 lanes instead of 4. So let's look at this picture here. Actually, let's do an example first. When we have 2 different reactions. So here we have an energy diagram for a 2-step mechanism. Now, our step 1 is slower or faster than our step 2. So notice again, you have your reactants and you have your products. This is an exothermic reaction because more energy was going down as the reaction moved forward. You have 2 humps, right? Because there's 2 steps, so they both have an activation barrier. Now, which of these steps is slower? The first one, right? How do you know that it's slower? Because the activation barrier is larger. So since the activation barrier is larger, it means that it would take longer to get through to the products. So step 1 has the higher activation energy, which then means it has a smaller rate constant, which is why it goes slower. And therefore, that is the rate determining step. That's your slow step. And so step 2 is your fast step. It's kind of a way that you can use graphical measurements to figure it out from the graph. So again, the elementary steps in the mechanism must sum up the overall reaction, and the rate law predicted by the mechanism must be consistent with the experimentally observed rate law. When you're looking at an energy diagram, we know that the slower step will always have the larger activation energy, which gives us our smaller rate constant and means that's the rate determining step. Now, let's actually do an example. So giving myself some white space here. So let's say that you have NO2 plus NO2 is NO3 plus NO. This is a slow step. Then we have NO3 plus CO makes NO2 plus CO2, and this is the fast step. What does this sum up to overall? Well, the NO3s cancel out. The NO2s cancel out. You're left with nitrogen dioxide. 2 of the NO2s cancel out. Nitrogen dioxide, carbon monoxide, and nitrogen monoxide and carbon dioxide. This is our overall reaction. Awesome. So you just determined the mechanism. Now, what about the rate law? So you write the rate law in terms of the slow step. So the rate law would be rate is equal to the rate constant times nitrogen dioxide squared. What are my intermediates? Well, my intermediate, do I just have one or do I have more than one? What's my reaction intermediate? Just nitrogen trioxide, because nitrogen trioxide formed and was then consumed. Awesome. So that's just when you have 2 steps, summing it up, finding the rate law, figuring out what the reaction mechanism is. Now what I want to do is look at a reaction mechanism when you have a fast initial step. So, for example, we have the following reaction. We have 2NO with our fast initial step, and it's an equilibrium. Now, this happens because when you have a very fast initial step, what does a double arrow mean? It means that as the product is forming, it's so fast that it decomposes back to the reactants. So it's in equilibrium. Then you have a slow step. And then you have another step. So you have a 3-step mechanism, and your initial step is fast. So now I would ask you, write the overall equation. All right, let's determine that. Well, my N2O2 goes away, and my N2O goes away, and I have 2NO plus 2H2 makes 2H2O plus N2. Awesome. All right, so then my question would be, what are the intermediates? What do I have? N2O2 and N2O. Awesome. Now, write the rate law. So rate is equal to slow step, right? So K2 times the reactants. So just like what we did in the other example. So here in the other example, this is where we stopped. But this is where we can't stop. And the reason for that is because what do you notice about your reactants? N2O2 is an intermediate. Therefore, it's not consistent with actually telling us the experimentally observed rate law because it gets produced and then consumed right away. So we have to solve for the intermediate and use that in our rate law to give us our actual accurate rate law for this step. So this always happens when you have an intermediate in your rate equation. So I have to solve for N2O. Well, where is N2O? Oops, no, let's not do that. Let's just go back to black. So I noticed that in my first equation is where my dinitrogen dioxide is actually formed. So since this is equilibrium, that's also like an equal sign. So I would write that I have my forward reaction is equal to, the rate is equal to K1 times NO squared. Now, we usually do not use the exponent as a coefficient, but since this is a mechanism and we're thinking of how many of the substances we have, we use the exponents and coefficients as one. And then for the reverse reaction, we have that the rate is equal to K inverse 1, which is the opposite process of N2O2. Now, because they're in equilibrium, the forward reaction equals the reverse reaction. So then K1 is equal to NO squared, K negative 1 is equal to N2O2. Now, because we don't want our intermediate, we're solving for our intermediate. So you divide both sides by K inverse 1, and then N2O2 is equal to K1 over K negative 1, it's not negative 1, but K sub 1, NO2, NO squared. Then you would use this back in your original rate law. So then rate is equal to K2 times H2, K1, K negative 1, NO squared. Now we can simplify this and make it look prettier and say K2, K1, K inverse 1, H2, NO squared. The reason we had to do this was because, again, our rate limiting step tells us exactly the rate that this reaction will occur. It's the most honest because it takes into account the slowest amount of the reaction. Well, this actually had an intermediate in it. Because an intermediate is consumed right away, it doesn't give us the accurate rate law. So then you have to look at your mechanism and solve for the intermediate. If you're using your really fast initial step, since it's at equilibrium, the forward and the reverse reaction are equal. You set them equal to one another and solve for your intermediate. Then you use that to go back to your original rate law and simplify. Now we can simplify this a little bit more, and I can say that I'm going to say K is equal to K2, K1 over inverse of K. So then rate would be K is equal to H2 NO squared. Another thing, when you have, just like we say, if you have A plus A, we say that rate is equal to KA squared. Just like if you have 2A, we would say the rate is equal to KA squared. Since this is a mechanism, we're taking into account all of the coefficients to know exactly how much we have of each. So this is where you find the rate law using the slow step like we did in the previous example when you have a fast initial step and when you have an intermediate in your rate law because you don't want that.